It's the most powerful technology of our time. But how does artificial intelligence actually work? We're pulling back the curtain. This is AI Deconstructed.
In our last episode, we assembled the architecture of a modern neural network. We stacked layers of perceptrons to create the multi-layer perceptron, or MLP, giving our network the depth it needed to solve complex nonlinear problems like the XOR puzzle. We saw how this architecture, with its inputs, hidden layers, and outputs, all connected by weights and biases, forms a powerful, flexible machine. But we left it in a state of suspended animation. We built the structure, but we didn't give it life. The weights and biases, the billions of knobs and dials that determine the network's behavior, were all set to random initial values. As it stood, our MLP was an engine, beautifully assembled, but with no fuel and no spark. Its answers would be complete garbage. What if I told you that the secret to artificial intelligence isn't about being smart? What if it's about being wrong, over and over again, but each time being just a little less wrong? Today, we're opening the hood on the learning engine of AI. We're going to explore the two remarkable algorithms that form a powerful partnership, allowing a machine to learn from its mistakes: gradient descent and backpropagation. This is the core mechanism that transforms a neural network from a blank slate, a jumble of random numbers, into a sophisticated tool that can recognize your face, translate languages, or even drive a car. When a neural network is first created, its internal parameters, millions of digital knobs called weights and biases, are set randomly. Its initial predictions are pure, unadulterated guesswork. The entire goal of what we call training is to intelligently adjust these millions of parameters to minimize the difference between the network's guess and the right answer. This methodical process of fine-tuning is called optimization. To understand this, we'll use the metaphor of a learning engine. This engine has two critical components working in perfect harmony. First, there's gradient descent, which acts as the navigator, or the strategist. It's the algorithm that decides the direction in which to adjust the parameters to reduce the error. It's the grand strategy for seeking the lowest point of error in a vast, complex landscape. But a navigator needs a map. That's where backpropagation comes in. Backpropagation is the chief engineer, or the mapmaker. It's the highly efficient mechanism that provides gradient descent with the crucial information it needs to navigate. Specifically, it calculates the slope of the error landscape at any given point, telling the navigator which way is down. Over the next 30 minutes or so, we'll unpack this engine piece by piece. We'll start with the destination, understanding what we're trying to minimize. Then, we'll join a blindfolded hiker on a foggy mountain to understand gradient descent. After that, we'll step into a corporate boardroom to see how backpropagation assigns blame. And finally, we'll see how this engine, born from decades of research, now powers the world around us. Before we dive into how a network learns, we need to be crystal clear about what it's trying to achieve. The abstract goal of minimizing error needs to be made concrete. This requires understanding the network's scoreboard and its control panel. Imagine you're playing the hot or cold game. You're trying to find a hidden object, and with every guess, someone tells you warmer or colder. A loss function, also called a cost or error function, is the AI equivalent of that guide. It provides a single, precise number that quantifies exactly how wrong the network's prediction was. Technically, the loss function compares the network's predicted output with the correct answer, the ground truth label from the training data. If the network's prediction is very close to the truth, the loss is a small number. If the prediction is wildly inaccurate, the loss is a large number. The entire training process is a relentless quest to make that loss number as small as possible. The choice of which loss function to use is critical and depends entirely on the task at hand. This is a key point. Error is not a universal concept. It must be defined specifically for the problem you're trying to solve. For a regression task where you're predicting a continuous value like the price of a house, a common choice is mean squared error, or MSE. Let's imagine that simple task. We're training a network to predict house prices. Our network takes in features like square footage, number of bedrooms, and location, and it's supposed to output a price. Our network sees its first house. Based on its random, untrained weights, it predicts a price of $150,000. But we know the actual selling price for this house, the label, was $400,000. The error is enormous, but how do we quantify it? We could just subtract. 150,000 minus 400,000 is negative 250,000. For another house, it might predict 500,000 when the real price was 400,000, an error of positive 100,000. If we just add those errors, the positive and negative values might start to cancel each other out, making our network look good on average when it's actually terrible. We need a way to make all errors bad, regardless of their sign. The solution, MSE, calculates the average of the squared differences. It takes the error, prediction minus actual value, and you square it. In our first example, the error was negative 250,000. Squared, that becomes a massive positive number. In our second example, the positive 100,000 when squared also becomes a very large positive number. This squaring trick does two brilliant things. First, it makes all errors positive, so they accumulate instead of canceling out. A high MSE is definitively bad. A low MSE is definitively good. Second, by squaring the error, it punishes large errors far more than small ones. An error of 10 becomes a loss of 100, but an error of 100 becomes a loss of 10,000. This gives the network a powerful incentive to fix its biggest mistakes first. The mean part of mean squared error just means we calculate this squared error for every house in our dataset, add them all up, and then divide by the number of houses to get the average squared error. This gives us our single critical number, the loss. For a classification task like identifying an image as a cat or a dog, the goal is different. Here, you might use cross-entropy loss. Let's stick with a spam or not spam example. Our network's final neuron, as we learned last episode, will probably use a sigmoid activation function to output a number between 0 and 1. We interpret this as a probability. An output of 0.9 means 90% confident this is spam. An output of 0.05 means 5% confident this is spam, or rather 95% confident it's not spam. The actual label is either 0, meaning not spam, or 1, meaning spam. Cross-entropy loss is a concept from information theory. The best way to build an intuition for it is to think of it as a measure of surprise. It measures how surprised our loss function is by the network's prediction, given what the true answer was. Let's say the correct answer is spam, which is a label of 1. If our network predicts 0.99, meaning it's 99% sure it's spam, the cross-entropy loss is tiny. The loss function is not surprised at all. It says, "Good job, you were very confident, and you were right." Now, what if the correct answer is still spam, label 1, but our network predicts 0.5, it's on the fence, 50-50. The loss function is more surprised. The loss value will be higher. It says, "You weren't sure, but you were at least leaning the wrong way." That's not great. Now the critical case. The correct answer is spam, label 1, but our network confidently predicts 0.01. It's 99% sure it's not spam. It's not just wrong, it's confidently wrong. In this case, the cross-entropy loss function explodes. It produces an enormous loss value. It is infinitely surprised. It screams, "You were supremely confident about the exact wrong answer. This is a massive error that must be fixed immediately." This behavior is exactly what we want. We want a loss function that doesn't just nudge the network, but shouts at it when it makes confident, terrible mistakes. This is what makes cross-entropy loss so effective for classification tasks. This deliberate separation of the objective, the loss function, from the machinery that tries to achieve it reveals a core design principle in machine learning. It creates a modular system where you can swap out the objective without redesigning the entire network. This very modularity is what makes advanced techniques like transfer learning and fine-tuning possible. A model pre-trained on a massive dataset has its parameters tuned for a general task. To adapt it to a new, specific task, you can simply swap out the final layer and the loss function, and then continue the optimization process. This fundamental separation is the enabler of much of the flexibility we see in modern AI. So, if the loss function is the scoreboard, what is the network actually changing to improve its score? The answer lies in its learnable parameters, the weights and biases. Imagine a giant, complex sound mixing board with millions of individual knobs and sliders. This is a great analogy for a neural network's parameters. Training the network is like a sound engineer trying to find the perfect setting for every single knob to produce a flawless piece of music. Weights are the most numerous knobs. Each connection between neurons in a network has a weight, which is just a number that determines the strength or importance of that connection. A connection with a large positive weight means the signal from the first neuron has a strong excitatory influence on the next. A large negative weight implies a strong inhibitory influence. A weight near zero means the connection is weak and has little effect. You can think of it like a professor who weights the final exam more heavily than the homework assignments when calculating a final grade. Biases are a different kind of knob. Each neuron has a single bias value associated with it. A bias acts as a baseline activation, making it easier or harder for a neuron to fire. It provides flexibility by allowing the neuron to activate even if its weighted inputs are zero or weak. An intuitive way to think of a bias is as a thumb on the scale, giving a neuron a little push to be more or less active by default, independent of its inputs. The goal of training, therefore, becomes beautifully simple in concept, yet mind-bogglingly complex in practice. Find the exact setting for every single one of these millions of weight and bias knobs that results in the lowest possible average score from the loss function. When evaluated across the entire training dataset, the question is, with millions of knobs, how on earth do you know which ones to turn and in which direction? For that, we need a navigator. To solve this monumental optimization problem, we use an algorithm called gradient descent. It is one of the most important algorithms in all of machine learning, forming the foundation for training everything from simple linear models to the most complex deep neural networks. The best way to build a deep intuitive understanding of it is with a powerful analogy. Imagine you're a hiker, blindfolded, standing somewhere on a vast, foggy mountain range. Your mission is to find the absolute lowest point, the deepest valley. You can't see the whole map, the fog is too thick. All you can do is feel the slope of the ground directly under your feet. This scenario maps perfectly to the challenge of training a neural network. The hiker's position on the mountain represents the current settings of all the weights and biases in the network. Since there are millions of parameters, this is a million-dimensional mountain. but the analogy holds. The altitude at the hiker's current position is the value of the loss function. A high altitude means a high error. A low altitude means a low error. The deepest valley on the entire mountain range is the global minimum, the specific combination of weights and biases that produces the lowest possible error. So what's the strategy? It's simple. From your current position, you feel the ground in all directions and find the direction of the steepest downhill slope. Then you take a small step in that direction. You repeat this process over and over. Feel the slope, take a step downhill, feel the slope again, take another step. Eventually, this iterative process will lead you to the bottom of a valley. This is the essence of gradient descent. To execute this strategy, our hiker needs two essential tools: a compass to find the direction and a way to decide the size of their step. Tool 1. The gradient. This is our compass. In the language of calculus, the direction of the steepest slope is given by the gradient. The gradient is a vector, a list of numbers that points in the direction of the steepest uphill ascent from your current position. Each number in the gradient vector corresponds to one of the network's parameters, a weight or a bias, and tells us how the loss would change if we were to nudge that specific parameter. Since the gradient points uphill, the strategy for our hiker is simple. Calculate the gradient and take a step in the exact opposite direction. This direction, the negative gradient, is the direction of steepest descent, the most efficient path downhill from the current point. Tool 2. The learning rate. This is our step size. Knowing the direction is only half the battle. The hiker also needs to decide how big of a step to take. This is controlled by a hyperparameter called the learning rate. It's a small number that we multiply the gradient by to determine the size of our update. Choosing the right learning rate is a classic Goldilocks problem and is one of the most critical decisions in training a neural network. If the learning rate is too large, our hiker takes giant leaps. They might be so large that they completely overshoot the bottom of the valley and land on the other side at an even higher altitude. This can cause the training process to become unstable, with the loss bouncing around erratically and never converging. If the learning rate is too small, our hiker takes tiny, cautious shuffles. While this is a safe strategy that will eventually lead to the bottom, it can be painfully slow. For a network with millions of parameters and a massive dataset, a learning rate that is too small could mean the training process takes weeks, months, or even longer to complete. Finding the optimal learning rate often involves some experimentation, and advanced techniques even adjust the learning rate dynamically during training. The final piece of the gradient descent puzzle is deciding how much of the mountain to survey before taking each step. This leads to three main variants of the algorithm. First is batch gradient descent. This is the most cautious and methodical hiker. Before taking a single step, they survey the slope over the entire mountain range. In machine learning terms, the algorithm calculates the gradient based on the entire training dataset before updating the weights. This gives a very accurate, true gradient of the overall loss landscape. However, for modern datasets with millions or billions of data points, this is computationally infeasible. It would require loading the entire dataset into memory and performing a massive calculation for just one step, making it incredibly slow. Second is stochastic gradient descent, or SGD. This is the most impulsive and erratic hiker. They don't survey anything. They take a step after feeling the slope of just one single pebble under their foot. In machine learning terms, SGD updates the weights after processing just one single training example. This process is much faster per update. However, the path it takes is very noisy and chaotic, zigzagging wildly as it's pulled in different directions by each individual data point. This randomness isn't all bad though. The noisy steps can sometimes help the hiker jump out of shallow valleys or local minima that a more cautious approach might get stuck in. Third is mini-batch gradient descent. This is the pragmatic compromise, and the method used almost universally in modern deep learning. Our hiker doesn't look at the whole mountain, nor just one pebble. Instead, they check the average slope of a small patch of ground, a mini-batch, of say 32, 64, or 256 training examples, before taking a step. This approach strikes a beautiful balance. It's far more computationally efficient than batch gradient descent, and its gradient estimate is much more stable and less noisy than SGD, leading to a smoother convergence. This trade-off between the variants reveals a fundamental truth about modern AI. The field is built not on perfect, exact calculations, but on efficient approximations. We almost never compute the true gradient. Instead, we rely on these good enough stochastic estimates from mini-batches to make rapid iterative progress. The noise inherent in this process, once seen as a bug, is now often understood as a feature, a source of randomness that helps the optimization process explore the landscape more effectively and avoid getting easily trapped. The entire field is built on this foundation of computationally tractable approximation. Now we have our navigator, gradient descent, ready to find the path downhill, but it's still missing its map. How does it actually calculate the gradient, the slope of a function with millions of parameters? For that, we need to enter the engine room. If gradient descent is the strategy for minimizing error, backpropagation is the ingenious tactical algorithm that makes the strategy possible. Its full name is backward propagation of errors, and it is the standard algorithm for training most neural networks. It is, quite simply, a remarkably efficient way to compute the gradient of the loss function with respect to every single weight and bias in the network. To grasp the intuition behind backpropagation, let's leave the mountains and step into a corporate boardroom. Imagine a large corporation launches a new product, and the sales numbers are a disaster. The final result, the output, is terrible. The CEO, whose only concern is the final profit number, the loss function, is furious and needs to know who is responsible for the failure. A naive CEO might just fire everyone, but that's inefficient. A smart CEO performs a post-mortem, a systematic process of assigning blame proportionally. This is exactly what backpropagation does. Let's map the analogy. The CEO is the loss function, which only sees the final error, the corporate hierarchy, from the sales team at the end, back through marketing, to product development, to the initial research team, represents the layers of the neural network. The individual employees at each level are the neurons, and their influence on their department's output is determined by their weights. Backpropagation is the process of the CEO starting with the final bad result, the high loss, and working backward through the company, layer by layer. It starts with the sales team, the output layer, and asks, how much did your actions contribute to this final error? Then it moves to the marketing team, the next layer back, and asks, given the blame assigned to the sales team and knowing how your marketing materials influence their performance, how much of the blame belongs to you? This process continues all the way back to the earliest layers of the company, calculating precisely how much each individual employee's contribution, each weight, ultimately affected the final outcome. This process of assigning blame might sound abstract, but mathematically, it is nothing more than a clever and highly efficient application of the chain rule from calculus. The chain rule, allows you to calculate how a change in an initial variable affects a final outcome through a series of intermediate steps. In our corporate analogy, the chain rule is the mathematical tool that allows the CEO to quantify how a small decision made by a junior engineer in the product development department, an early weight in the network, ultimately impacted the final sales number, the loss, by tracing its effect through every intermediate manager and department it influenced along the way. The absolute genius of backpropagation is that it is a local process. An employee in the marketing department doesn't need to understand the entire corporate structure. They only need to know two things. One, how their own actions directly affect their department's output, their local gradient, and two, how much blame their direct manager from the sales department passed down to them, the gradient from the next layer. By multiplying these two pieces of information, they can calculate their own share of the blame and pass the appropriate amount onto the product development team that reports to them. This locality, this cascade of responsibility, is what makes backpropagation so computationally efficient. This efficiency is not a minor detail. It is the primary reason deep learning is feasible today. A naive approach of calculating the effect of each weight on the loss independently would require a separate forward pass through the entire network for every single parameter. For a model with 1 million weights, this would mean 1,000,001 forward passes. Backpropagation achieves the exact same result in just 2 passes, 1 forward pass to get the prediction, and 1 backward pass to calculate all the gradients. This is not just an improvement, it's a transformation of the problem's complexity. This is because backpropagation is, at its heart, a dynamic programming algorithm. The chain rule is a mathematical fact that is centuries old, but backpropagation is the specific algorithm that implements it efficiently for networks. It avoids redundant calculations by starting at the end and reusing the results from one layer to compute the gradients for the layer before it. This is the hallmark of dynamic programming, solving a complex problem by breaking it down and storing the solutions to subproblems. This algorithmic insight transformed an exponentially complex problem into a linearly complex one, unlocking the ability to train the massive networks that define modern AI. Let's put it all together and walk through a single iteration of the learning process, the 4-step dance that trains a neural network. Step 1. The forward pass. We take an input from our training data, say an image of a cat, and feed it into the network. The signal propagates forward from the input layer through all the hidden layers. At each neuron, the inputs are multiplied by their weights. The bias is added, and the result is passed through an activation function. This continues until the output layer makes a final prediction, for example. I'm 80% sure this is a dog, and 20% sure it's a cat. Step 2. Calculate loss. The network's prediction, 80% dog, is compared to the true label, 100% cat. The loss function then calculates the error, spitting out a single number that represents how wrong the prediction was. Step 3. The backward pass. This is backpropagation. This is where the learning begins. The error signal starts at the output layer and flows backward through the network. Using the chain rule, the algorithm efficiently calculates the gradient of the loss with respect to every single weight and bias. This is the blame assignment step, determining how much each parameter contributed to the final error. Step 4. Update weights. This is gradient descent. Now the navigator takes over. The optimizer, gradient descent, receives the map of gradients from backpropagation. It takes these gradients, multiplies them by the learning rate to determine the step size, and updates all the weights and biases in the network, nudging each one slightly in the direction that will reduce the error. For each weight, the new weight becomes the old weight minus the learning rate times the gradient for that specific weight. This entire four-step cycle is one training iteration. It is repeated thousands or even millions of times, using mini batches of data. With each cycle, the network's internal parameters are refined, and its predictions get incrementally, painstakingly, a little less wrong. Now that we've built the engine, let's fine-tune our understanding by addressing some common points of confusion and exploring a more modern, nuanced view of how this process works in the wild. One of the most common misconceptions for beginners is to think that gradient descent and backpropagation are the same thing, or to use the terms interchangeably. They are not. They are two distinct algorithms that form a perfect partnership, a beautiful division of labor. The clearest way to remember their roles is with this analogy. Backpropagation is the intelligence agency that gathers the intel. Gradient descent is the field agent that acts on that intel. Backpropagation's sole job is to efficiently calculate the gradients, to create the map of the error landscape. It tells us the slope. Gradient descent's job is to use those gradients to update the network's weights. It's the navigator that follows the map. Backpropagation serves gradient descent. One cannot do its job without the other in the context of training neural networks. For decades, one of the biggest theoretical fears in machine learning was the problem of local minima. In our hiker analogy, this would be getting stuck in a small valley or divot that isn't the absolute lowest point on the entire mountain range. The algorithm, only looking at the local slope, would find the bottom of this shallow valley, see that every direction is uphill, and mistakenly conclude that its job is done, when the much deeper, true global minimum is just over the next ridge. However, one of the most surprising and profound discoveries in modern deep learning is that for the kinds of problems we're solving, this fear is largely unfounded. In the incredibly high-dimensional spaces of neural networks, true, isolated local minima are surprisingly rare. The intuition is fascinating. For a point in a two-dimensional or three-dimensional space to be a local minimum, the surface just has to curve upwards in 2 or 3 directions. But for a point in a million-dimensional space to be a local minimum, the loss surface must curve upwards in every single one of those million dimensions simultaneously. The probability of this happening is vanishingly small. The more common obstacle in these high-dimensional landscapes is a saddle point. A saddle point is a point where the gradient is 0, but it's a minimum in some dimensions and a maximum in others, like the center of a horse's saddle. Basic gradient descent can slow down or get stuck on the flat plateaus around these saddle points. However, more advanced optimizers, which we will discuss in a future episode, incorporate concepts like momentum. Imagine a heavy ball rolling downhill that can easily coast over flat spots and small bumps, which are very effective at navigating saddle points. Furthermore, research suggests that for very large networks, most of the local minima that do exist are of very similar quality. That is, their loss values are almost as good as the loss of the true global minimum. Finding a good enough solution is often sufficient for excellent performance. In fact, aggressively searching for the absolute global minimum can sometimes be a trap, leading the model to overfit, to memorize the training data perfectly at the expense of generalizing to new, unseen data. This entire phenomenon represents a beautiful reversal of conventional wisdom. The curse of dimensionality, which often makes problems harder as dimensions increase, becomes a blessing of dimensionality in the context of optimization. The sheer vastness of the parameter space creates more escape routes from any given point. The very complexity that makes neural networks so powerful is also what, counterintuitively, makes their optimization landscape more navigable than we once feared. These algorithms didn't appear in a single flash of genius. They are the product of a long, multidisciplinary evolution, with key ideas lying dormant for years before the right conditions allowed them to flourish. The story begins in the 1950s and 60s with the perceptron, an early model of a single neuron. While promising, it had severe limitations, famously being unable to solve simple nonlinear problems like the XOR logic function. This failure, highlighted in the 1969 book Perceptrons by Minsky and Papert, led to a loss of funding and the first AI winter. Researchers knew that multi-layer networks were more powerful, but they had no effective way to train them. The crucial breakthrough came quietly. The modern, efficient version of the backpropagation algorithm, then called reverse-mode automatic differentiation, was first published by a Finnish master's student named Seppo Linnanmaa in his 1970 thesis. However, his work was in applied mathematics and made no connection to neural networks. That connection was made independently by Paul Werbose in his 1974 PhD thesis, which wasn't published until 1982. He proposed that this efficient backward propagating method could be the key to training multi-layer neural networks. Despite these origins, the idea didn't catch fire until 1986. A seminal paper by David Rumelhart, Geoffrey Hinton, and Ronald Williams, titled Learning Representations by Backpropagating Errors, provided a clear explanation and powerful demonstration of the algorithm's capabilities. This paper brought backpropagation into the mainstream of cognitive science and machine learning, sparking a connectionist revival. The final piece of the puzzle was a practical, real-world application. In 1989, Jan LeCun, working at Bell Labs, successfully applied backpropagation to train convolutional neural networks, or CNNs, to recognize handwritten digits. This system was eventually deployed to read a significant percentage of all checks in the United States, proving that this learning engine could solve complex, commercially valuable problems. This history reveals a powerful lesson about innovation. The core algorithm for backpropagation existed for over a decade before the necessary computational power and community recognition aligned to unlock its revolutionary potential. In the 1970s, compute was billions of times more expensive and slower than it is today. The popularization in the mid-80s coincided with the rise of more accessible computing. A brilliant algorithm is not always enough. Its impact is often gated by the technological and social ecosystem it inhabits. So, the next time you think about how an AI learns, remember our two key players. Remember the blindfolded hiker, gradient descent, feeling for the downward slope, carefully choosing the size of each step to find the bottom of the valley of error. And remember the corporate post-mortem backpropagation, the engine of accountability that efficiently traces the error back from the final result to every single parameter, figuring out exactly how to make things better next time. This two-part engine is not just a clever piece of math. It is the fundamental mechanism that transformed neural networks from a theoretical curiosity into the driving force of the modern AI revolution. It is at work all around us, every day. When your phone's photo app automatically tags your friends, a convolutional neural network, trained with this very engine, is minimizing the error in classifying pixels that make up a face. When you use a translation service or interact with a sophisticated chatbot, a transformer model has been trained using backpropagation and gradient descent to adjust billions of weights, all to get better at predicting the next word in a sentence. When an autonomous vehicle identifies a pedestrian or a stop sign, it's because this learning engine has optimized the network's parameters over millions of miles of simulated and real-world driving data. This process, a forward pass, a loss calculation, a backward pass, and a weight update, is the heartbeat of deep learning. It is the process that allows a machine, in a very real mathematical sense, to learn from experience. We've built the engine and its fuel system, but we've been hand-waving one crucial component. During the backpropagation step, I mentioned that the blame is multiplied by the local gradient of each neuron's activation function. It turns out the mathematical properties of these activation functions are not a minor detail. They are everything. The slope of the activation function is what backpropagation multiplies at every single step. If that slope is 0, the blame vanishes. The gradient becomes 0 and learning stops cold. This is the famous vanishing gradient problem. To build a deep network, we need an activation function whose gradient is reliable, stable, and fast to compute. The sigmoid function we've used so far fails this test. The real spark-plug of the modern AI engine is something far simpler and far more powerful. In our next episode, we explore that spark. We dive into the world of activation functions, and we'll see how a function as stunningly simple as, if the input is negative, output 0, completely unlocked the deep learning revolution.
You've been listening to AI Deconstructed. Join us next time as we unpack another layer of the technology shaping our future. Until then, stay curious. Subscribe for more.